Yes, now we have a talk from... blank. This is why I'm the professional. We have a talk from people with names up on the screen. I could have just glanced at it. They'd never have known that I went blank. But I didn't do that because I'm honest or useless. Pick one. From James Macfarlane, Edinburgh, who are going to be talking about, well, this. And I have a feeling that this is going to be loud. So, if anyone is of a nervous disposition, cower in a corner. Big round of applause, please.
Well, I'm Ed and James is just sitting down there. So we both work in rocket propulsion, and we're going to talk a bit about rocket propulsion, what there actually is to research in it. And then at the end, we've got this little demonstration engine we make to show schools and stuff, so we're going to find out. We'll probably go outside for it, because I think that the motor is sensitive to heat. So, normally in general interest talks, you're not meant to sort of do too much maths, but because it is a talk about rocket science, I want to do one equation with you, if that's all right. And it's a really elegant and simple one that governs most of what we do, and it falls out of a very important and simple concept in the universe, which I'm going to illustrate now. So I want you to look at what the cannon does when it fires it. I'll show you that again just for fun. So the cannon actually goes back when it fires a cannonball. And this is because of the principle of the conservation of momentum. So the total amount of momentum in the universe has to stay the same always. So if the cannonball, if the gun projects a cannonball which has a mass and it projects it out at a certain speed, then that same amount of mass times speed, momentum, has to go back into the cannon in the opposite direction, so the total amount of momentum is conserved. And the principle of the rocket is exactly that. It's that we exploit to generate a force. So if we take a sort of toy rocket here, and it's just going along in space, it's got some mass and it's got some velocity. And then a tiny bit later, it wants to increase its speed. So like a cannon, it ejects a little lump out of the back of itself. And it in turn gets a bit of momentum imparted back into it and sends it forward. And the thing to note is that the total amount of momentum here is exactly the same as the total amount of momentum here. So we can label up what's happened. The letter D just means a tiny amount of something. So here, the mass is the original mass minus a little bit. It's going at the original velocity plus a little bit more velocity, and we've ejected a little bit of mass out the back with a certain velocity E, exit velocity. You can write that down algebraically, and it's just saying that mass times velocity and momentum on this side is exactly the same as the mass times velocity on this side. So we've got slightly less mass with slightly more speed. And then you've got to factor in the speed you've projected off, which is minus a bit of the same velocity minus the exhaust velocity and a little bit of mass. If you multiply this all out, loads of it simplifies and goes away, and you get this simple differential equation. If you remember calculus, you might understand what happens next. If not, don't worry. We can basically just put in our sort of beginning and end conditions. So we can say we start off with some known total amount of mass. And when the rocket's empty, it's just the sort of shell and leftover bits, so that's the final mass. So we can do what's called integration to solve this differential equation between an empty mass and a full mass, E for empty and full, blah, 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 blah. What you end up with is one of the most important equations in rocket science, the so-called rocket equation. And it basically says that the total amount of the change in speed you can give yourself, so that's delta V, the change in speed, is equal to two things. One is the exhaust velocity, so how fast you can project stuff out the back. And the other thing is the ratio, I'm not sure if you can quite see this at the back, but it's the ratio of the final mass over the full mass over the empty mass. So the full mass of a rocket might be 100 kilos, the empty mass might be 10 kilos, so that ratio would be 10. And this little natural log thing just means that you sort of get a law of diminishing returns as this number gets bigger. So if you wanted to increase this speed by a little bit, you might have to increase this mass ratio by quite a lot, which is one of the reasons that making rockets go even faster is hard. But the point is, it boils down to two things: how fast we can eject stuff out the back, and the total amount of mass that is propellant in the rocket that takes off. So the next question might be, what are we going to lob out the back in order to get this momentum exchange? Or you could sort of do the cannon type thing and keep on firing things out the back. And in fact, people have actually tried that. This was back in the 60s. It's a rubbish video, but you can hopefully see that they're sort of firing stuff out the back. I mean, it sort of works, but it wouldn't be much fun for the people on board if they were. Another approach is to, instead of lobbing a few discrete heavy things out the back, you could just lob millions and millions of much lighter things a bit faster out the back to get the same effect. So we've all seen this before, but so if I create some pressure inside here, it's at a higher pressure on the inside than on the outside. So when I let go, the air molecule is going to be accelerated out the back, just like that. You could get more bang for your buck if you increase the pressure inside the balloon. So when we go and talk to schools about how rocket propulsion works, sometimes we made this little skateboard that we power by a fire extinguisher, and this is Ian riding a skateboard. So we get a pipe from the skateboard and just run it to a little nozzle we had to make at the back, and that vents out the front. But that was about a kilogram or two of carbon dioxide, and it only increases your speed by sort of 5 to 6 miles an hour. It's actually quite inefficient. And it turns out that we have to turn to chemistry to get the most amount of energy for a given weight of stuff. And almost all, apart from some nuclear research, almost all rockets done so far have been chemical. So what does a chemical rocket look like? Well, it is a sort of cartoon to illustrate it. We need two things in order to burn. We need a fuel and an oxidizer. In a jet engine, they get the oxidizer from the oxygen in the air, but obviously in a rocket you're in space, so you need to have both parts of the combustion equation. They get injected into what's called a chamber. There's quite a lot of science in getting that injector right, because you want to get everything well mixed, because if it's not well mixed, you're going to get unmixed stuff out the back, and that's a waste. What happens is, when the chemicals react, they don't really produce lots of nice, molecules going in a straight line. They just produce loads of heat. And what happens in the chamber is we produce loads of heat. And when you heat up gases, you get lots of pressure. So there's a sort of little explosion in there to demonstrate. And what we then have to do is sort of take all this energetic stuff going in the combustion chamber and somehow turn it into the momentum exchange we want. Now, just to show you that I'm not making this up, here's a real rocket engine, which is roughly the same shape. This is the Space Shuttle main engine. You can see actually buried right in the middle there is the combustion chamber. There's a huge amount of peripheral stuff. And here's the nozzle. A lot of the peripheral stuff is actually pumps. One of the things you have to do with the rocket engine is, if you can imagine you're having a sort of an explosion in a combustion chamber, that's at quite high pressure. In order to inject fuel and oxidize it into the chamber, it has to be at even higher pressure. So you have these enormous and quite complicated pump systems to try and get the pressure up. You might just say, why not just have pressurized tanks? Well, if you did that for your fuel and your oxidizer, if you just had high pressure in your tanks, the tanks would have to be that much stronger and therefore be that much heavier, and that cuts into your mass fraction we talked about earlier, which means you can't get as much change in velocity. So they tend to have these pumps. This pump, for reference, is about the size of a dustbin, and it's about 80,000 horsepower on the Space Shuttle engine, so they're quite impressive bits of engineering. But they're just to inject the fuel in. And then often also the fuel is sort of sent on a loop. I'm not sure if you can see, but there are lots of little tubes at the bottom here. The fuel is often sent on a loop around the walls of the chamber and nozzle in order to keep it cool and stop it melting, because the temperatures are very high. So a lot of people think that this bit is the engine. Really, the combustion's happening in here. The nozzle is, as I said, to try and kind of shape the flow in a way we want to actually get some useful momentum. So we can do a simple sort of diagram to explain why it's necessary. If we didn't have a nozzle, if we chopped this off, you'd have a combustion chamber full of very high pressure gases as a result of a reaction. So we're going to call that pressure C for combustion chamber. Outside, it's atmospheric pressure, and atmospheric pressure is much less than the combustion chamber pressure. So if you were to just have a hole in the back, then all the gas would want to sort of come out in every direction, much like if you burst a balloon at higher pressure, all the gas molecules come out in every direction, they don't come in some specific direction. And why is that a problem? Well, if we just consider a slug of gas, so for example a bit of gas coming out this way with some velocity, well, we can split up its velocity to analyse it into a horizontal component and a vertical component. So the horizontal component is fine, it's going that way, which means, because momentum's a vector, we get a conservation of momentum giving us a thrust back that way. But it's also got a vertical component, which gives us a thrust down that way, which we don't want. But it's, because this is symmetric, you get the same thing on the other side. So these horizontal components of velocity summon together to give us more momentum that way. But these two cancel out. So what's happening is we're actually wasting potential momentum we could use to get more velocity in the direction we want by having these bits cancelling out, because the gas is just escaping. So what we do is we add in a nozzle which allows us to very carefully expand the gas until it's expanded to the point that the pressure at the exit is the same as the atmospheric pressure. If the gas is coming out at the same as atmospheric pressure, it has no desire to expand or contract or anything. It just comes out in a nice parallel sense. And that gives us the maximum momentum exchange back into the rocket. So that's the rocket science theory out of the way. I'm now going to hand over to James, who can talk about what we actually do in our laboratory research. Talk on this for a second.
So, Ed's told you a bit about the theory of rockets, so you've actually learned some rocket science for those that didn't already know it. So I'm going to talk a bit about how we actually test this in practice. What does it look like? Show you some video and some pictures of what we do. So Ed and I work for a company called Airborne Engineering, and one of our main bits of business is actually testing rocket engines. And what we do, sadly, we're not able to fire rockets around the countryside because Britain isn't really big enough for that. There's very few places you can do that. So we actually do what's called static testing most of the time. So we bolt the engine to a load cell, we measure pressures and temperatures and thrust. It's a bit like, if anyone's involved with car racing, it's a bit like putting an engine on a dyno. Exactly the same principle. So you need somewhere safe to do this, because even though we're not flying these things, it still makes quite a lot of noise and you need a secure establishment. So this is where we're based. This is actually a Second World War airfield, Westcott in Buckinghamshire. And it became a research establishment for rockets in the Cold War. And there were 1,100 civil servants all working on rocket technology. And in the 1980s it all got cancelled, they all got made redundant within that. It then became a business park. And I should say, of course, the reason it got cancelled was the end of the Cold War, which is a good thing. However, it does mean that we lost a lot of expertise in this country. A lot of these people retired, a lot of them actually no longer with us anymore. And so it's been a bit of a battle to actually try and learn from some of the old guys who were on this site and on other sites in the country who've been there and done that. And so this is our part of the site there. We've got a workshop here, a machine shop and offices and we've got these two test bays. This one belongs to another company we work with, and that belongs to Surrey Satellites, who do small satellites in space. And boom, there's a jellyfish. Surprise. I probably pressed the wrong button. Yeah. Okay, so let's it's a fail. Right. So one of our main customers is a company called Reaction Engines Limited, and they're the people behind this thing. This is a space plane. So the idea is that rather than a rocket taking off with a whole bunch of fuel vertically and then staging by separating different bits of it and throwing those bits away, which can really not be used again, this allows you to take off from a runway and fly into space with about 12 tons of payload, put it into space, and then fly back down again. And within a day, you can turn it around and do that again. And you can also fly people in space on this. And it's a very efficient green method of putting things in space. So it actually breathes the air while it's low down in the atmosphere. And it actually makes use of the air rather than something like Saturn V, whose job is just to punch through the air as quickly as possible and get into space where there's less drag. So we've done quite a lot of work on the rocket nozzles, which are the bit at the back of these two engines here, which propel the craft. And as Ed mentioned in his part of the talk, a lot of the way that we make rockets more efficient is governing how you direct the gases that come out of the combustion chamber. So the products of the combustion with something like Skylon, are actually just steam. In fact, it's water. It's water because it's hydrogen and oxygen. Or when it's in the atmosphere, it's actually just steam and nitrogen. So, but you've got to direct those gases somehow. And something like a Saturn V, which is the moon rocket that some of you may remember from the 70s. That rocket had the advantage that each stage could be optimised for the altitude that it was flying at. Skylon can't do that because it's one spacecraft. It doesn't stage, it stays in one piece, it's completely reused. So it can't throw anything away and change its geometry as it flies. It has to do everything with one set of engines. And so therefore we need a special shape on the engine that will compensate for the fact that the atmospheric pressure changes as you go from sea level on your runway and you take off and you fly into space where there's no air at all. And this engine was it's actually a funny acronym called STRIP, I don't know what it stands for, but it was to test the shape of the nozzle. And so people from Bristol University came up with a clever bit of computer code, which I think was actually in Fortran, strangely, to develop the shape of the nozzle. They then tested some small-scale models, and we were actually able to fire it on hydrogen and air to simulate a real Sabre engine. And hopefully I can actually show you that, a video of that in a second. So there's another view. You can see some of the instrumentation on this slide. You can see pressure taps here, and all these little tubes that come out are to measure the distribution of pressure along the nozzle wall, and that allows you to work out what the pattern of shock waves is in the rocket nozzle, and you can learn a huge amount about the shape and whether you've got it right or wrong, whether you just need to tweak it a little bit. So there's all sorts of valves and other things here which sequence the start-up and the running of the rocket engine. So hopefully, if I press this, we might get some video of this. It's a very, very short burn, this engine. So it's what's called a heat sink engine. It's a big lump of copper, and it saves us having to have those little cooling channels which Ed mentioned before on the space shuttle engine. They're really expensive to make, so it's much cheaper to have a big lump of copper and just fire it for a very short period of time before it melts. So here we go. Oh no, it's jellyfish. Richard jellyfish. Back to Portland. Right. Okay. There we go. Right, wait for it. So it's actually very, very short. You see a bit of flame at the beginning, and when it starts to burn properly, the flame becomes almost invisible because the exhaust is very, very clean. So if I do that, I can hopefully play that again without jellyfish appearing. That's the igniter going, that's down there. And that big loud noise is the main thrust portion of the engine. And even though that's about 800 milliseconds, 0.8 of a second, we've got a very fast data logging system, and we can gather as much data as we need to actually prove this concept, even in that short period of time. So this is another experiment that we did. It's related to Skylon. So someone said, well, if you've got these brilliant engines which can cruise in the stratosphere, how about rather than just carrying on to space, we stay in the stratosphere and we could fill it full of people, and then you could have a day ticket to Australia. You could go London to Sydney in 4 hours. And everyone I thought about this said, yeah, where do I sign up for a ticket? But sadly it's not there yet. So the EU is putting some money into studying what all the technological barriers are as to doing this project. One of them is, if you fly an air-breathing rocket engine in the stratosphere, it can deplete the ozone layer if you don't do something clever about it. Now, all engines which use air, even car engines, make nitric oxide, because some of the nitrogen in the air burns, and it actually gets chemically changed when it goes through an engine. It's not designed to do that, it's a sort of side effect. And you sometimes, when a car drives past, you can smell it, it's a sort of vinegary smell after the car's gone past. Now, at sea level, I think that's probably quite good for plants, but in the stratosphere it's really bad for the ozone layer. So we came up, well, our customer came up with a very clever shape to the inside of the nozzle, which actually regulates the temperature and makes sure the chemical reactions which cause pollutants don't actually happen. It's a very, very clever piece of technology, but it makes a very, very cool piece of video. I'll just explain what this is going to do. It's got a pre-combustor which makes a lovely big flame, big red flame come out the end. And then when the air comes in, so the pre-combustor is just hot hydrogen, when the air comes in, the flame will then become almost invisible, and you'll see a lovely pattern of shock diamonds here, which just show that the exhaust from the rocket is supersonic. They don't mean anything, technically, that you can measure, but they're quite beautiful things, and you'll see those appearing in some of the other bits of video that I've got to show you. So hopefully you won't get jellyfish. Now, here we go. So you'll hear the igniter first, and then you'll see the pre-combustor, which is the big flame, then you'll get the invisible flame. And there's the igniter, there's the pre-combustor, and now it's coming up to full thrust. You can just about see those almost invisible shock diamonds. So, in that video, hopefully I can just show you that one more time. shuts down with some hydrogen there, hydrogen right at the end. So other things we've been involved with are things, really blue sky things, like can you make propellant from the atmosphere of Mars? So if you send people to Mars, do you have to take all your rocket fuel with you to bring the people back, or a robot with a sample, or whatever it is? Or can you make the propellant on Mars so you don't need to take as much stuff with you? And that goes back to what Ed was saying about the mass fraction of the rocket, the full mass versus the empty mass. If you can actually make propellant where you've landed, then actually makes your life a lot easier. Everything becomes cheaper and easier. So we were trying to see whether we could burn carbon monoxide and oxygen efficiently to make a rocket engine. That combination is something that used to burn when people had town gas. That's before natural gas came in. It had hydrogen and carbon monoxide. So that combination is well known, but no one, to our knowledge, has really tried it in a rocket engine. We tried it, it actually works quite well. So here's a video of one of these tests. Again, it's a very short burn. So very, very, very fast. This is 750 milliseconds, so 3/4 of a second burn. So I just follow that again. You can just about see the shock diamonds when it shuts down. So if I wait for that video to stop, otherwise I'll get the jellyfish. And this one, the reason it's gone blank is this is what happens when you fire it at night, which is quite cool. So there we go, that's a night firing, that's saying. And this is a still shot that Ed took with a stills camera that actually shows this pattern of shock diamonds. You don't get this if you fire a rocket in space. This is a phenomenon that you get when you test a rocket at sea level. And it doesn't mean too much. It just shows that supersonic exhaust is slowing down and re-accelerating and slowing down and doing that until it runs out of momentum. But it's really quite a beautiful thing, and it's the sort of thing that gets rocket engineers out of bed in the morning. Now, we took that same engine and we modified it slightly for Cranfield University. So one thing that the European Space Agency said to the propulsion community in the UK is that there are not enough trained propulsion engineers. And so one of the universities in the UK, Cranfield, addressed this, and they set up a course to train people in rocket engine technology. Fortunately, we got a contract to actually build an engine so that their students could come and get hands-on training with what it's actually like to operate a rocket and to kind of predict its performance, go and fire it, get some data, look and see whether the results match up with the theory and see what you could do to perhaps improve the design. So hopefully this will actually run. Oh no, does that fire? It's actually, maybe I haven't got the video. No, okay. So no video. This is another thing we did.
Oh no, I think it does. I think it does.
Is it? Okay.
Press play or next. Leave it for a second.
Yeah. Oh yeah, yeah. Okay. So that's a bit of a longer one. That's nitrous oxide and isopropyl alcohol, those two plants. So they're very safe, benign things that are easy for people to handle without wearing all sorts of breathing apparatus and complicated stuff like that. So very safe, clean propellants. This is another engine we did. So if you want to make something that lands on another planet, like the lunar lander, and this is something that Europe's actually getting sort of interested in again after all these years since man went to the moon, and they're thinking, well, could we land a robot probe on the moon or Mars or something else like that? So we were looking into what you need to do that. And bear in mind, this has all been done in the 1970s. But in the UK and in Europe, we don't really have that technology so much these days because we don't have that direct sort of heritage. So we were looking at what you need to do that. And there's two things. You need to be able to change the thrust of the engine. So you need to throttle the engine up and down, a bit like a car engine. You don't just go at one speed. You need to be able to, as you land your rocket, to increase the thrust, to slow yourself down, and then reduce the thrust so that you actually sort of sit down gently on your lander. The other thing you need to be able to do with it is to steer the rocket engine to keep the rocket upright and stable, because otherwise a rocket without any other means of control will just go around in a loop. So this shows, this video shows a thrust vectoring, so it moves the whole rocket engine around using some linear actuators, and it's just pre-programmed in a fixed pattern, so it makes some nice ellipse on that plate. Hopefully this will play. So this could form a technology demonstrator for a future mission to another planet. So it's coming up to full thrust there. It's So it's just sweeping a fixed pattern. In reality, there'd be a feedback system that regulates the angle of the rocket to make it stable. Shuts down a bit of bang. So, in order to test rockets, you've got to be able to do a bit of everything. A bit of mechanical engineering, a bit of plumbing, in fact, a bit of hardware and a bit of software. And so we do other things as well, apart from, it's not all flash and bang, unfortunately, but we do get to play with some interesting bits of electronics. We do make our own instrumentation, our own data loggers. And we use a lot of open source tools and a lot of Linux-based stuff to do this. So we have an entire Linux-based data acquisition system that we built from scratch. We use GCC as a tool chain and all the ARM tools for the main CPU. So it's we do a lot of Linux and ARM and open source based work on all our instrumentation, and we've just built that similar system in a box that we can sell to other people like universities for doing instrumentation of their own little tiny rocket test rigs. So Kingston University in London just bought this system from us for their own little tiny rocket testing rig. So we've got a live demonstration to show you here, which Ed's going to set up. Now, the rockets I've shown you so far are called bipropellant rockets. So you put your fuel and your oxidizer, and you need both things to burn. Obviously, to burn anything, you need air and a fuel. So in a rocket, you need your fuel and oxidizer. It isn't necessarily oxygen, but usually something that makes oxygen. Or you can have something like a firework rocket, which is called a solid, where you have effectively an explosive which burns in a tube. This is a mixture of the two things. It's called a hybrid rocket. Something that's used a lot by people who do rockets as a hobby because it's quite safe and it's simple to use. It's got a plastic fuel grain, which is acrylic, so that's made of carbon, hydrogen and oxygen. And then we add in extra oxygen in the back through this injector, which is just a nozzle, and that then burns the plastic on the inside at a very high temperature and accelerates the gases out of that nozzle there, which generates a very small amount of thrust. Now, we've clamped it down to this table. It's not actually going to move that table. We'd be really, really impressed if it does. We designed this specifically to be very safe for school children, so we can take this in to demonstrate the students, and it's really quite fun. What you'll see is when we light it up, you'll see that a flame inside here that's really bright white, and then it'll start to burn the fuel. And so this will start to get bigger and bigger and bigger, and in a minute we'll pass around a spent fuel rod, so you can see what that looks like. And so it's just plastic, it's just acrylic that you'd use to make sort of hard printer. So you may want to put your fingers in your ears when it actually starts up. If there's anyone that can't put their fingers in their ears and wants some ear defenders, we've got some squishies in the cupboard there. So just let me know. But it's just fingers in the ears probably is fine. So you can see that a lot of rocket engineering is actually to do with plumbing. We think the fire alarm is building sensitive to heat as well as smoke, so that's why we're doing it outside. This is very clean, this engine, but we don't want to cause any trouble. So, just put the oxygen. So we've got a bottle of oxygen there, which is the same as you'd have on an oxyacetylene welding set. So it's standard industrial gas. And we're going to light it using an ordinary indoor fireworks sparkler that we just put up the end. And that provides enough heat just to get that plastic burning. And then Ed will then turn on the oxygen, and then you'll see it glowing in here and burning, and then we'll run it until we think it's sort of safe, and then we'll shut it down. It will burn Ed's water.
We'll probably need to speak about 4 or 5 seconds.
Yeah, okay.
We'll turn it off.
Yeah. You ready, Ed?
So.
Is everyone ready?
Yeah.
Right. I don't know how quickly you said that.
questions? Everyone's taking the fingers back out of their ears by now?
I have a question.
Oh, do you have a question? Oh,
it's slightly the exact way that you do that is it's partly analytical and also a lot of intuition and a lot of sort of experience. Yeah.
What do your kids think?
Well, I don't have kids, but we've taken this thing to a number of schools, and they absolutely love it. We've got some great letters back from them saying that they really, really love the rocket. I think they especially like Ian on the skateboard, actually.
Okay, I think that's all the time we have now, so a big thanks for James Ned for this.